Okay, welcome everybody to the introduction to spatial statistics with Python. It's great to see you all. Unfortunately, we're doing this virtually. Maybe it's fortunate for many of you because you don't have to come on campus. You don't have to find me in whatever room I'm teaching. I personally miss the in-person ambiance. It's not the greatest environment for me, but you know what? In the past year, this has actually been working really well. So I welcome you all to the workshop, and I'm going to start sharing my screen. And the moment I do that, everything moves around. So just 1 second, please. Let me bring up just Windows. Okay. All right. So once again, welcome. My name is Yo. I work for the Office of Advanced Research Computing at UCLA. I'm also on faculty in the Urban Planning Department and the Digital Humanities. And I teach spatial data science and GIS predominantly. Today's workshop, we're going to cover a very kind of introduction to spatial statistics using Python. My intention for today's workshop is to, as I mentioned, I'm not a statistician. I'm more of a GIS person and data visualization guy. What I want to do here is position you and yourself to be able to have the right tools and knowledge to advance your own research with kind of these methods that are completely in the open source community. So we're going to use tools like Python, Jupyter notebooks, and all these libraries that you can install and download and run on your own, although it's not easy. But what we have here today is we've set up an environment for you called the Jupyter Hub environment, which is free and available to all UCLA students. And I've also set up something called a binder notebook, which is also a web-based Jupyter notebook environment that is also free for you to use. Okay. Let me see. I welcome questions, even if it's during the workshop. I also welcome interruptions. I like to hear voices, so feel free to unmute yourselves at any time. If I'm going too fast, too slow, if I forgot something, I do that a lot. If I forget to share my screen, or if something is just not right, please unmute yourself and let me know. I'm going to do my best to keep my eye on the chat, but also I may miss something in the chat, so really just unmute yourselves and let me know. Okay, so let's get started. The website here includes a link. All the material, by the way, is in the repo, so you can come back here at any time. It will be up, forever, hopefully, and you'll be able to come back and access it. The recording will be available to you. We'll be sending a link to this recording, hopefully within a few days. And it'll go directly to your email as you've registered for the class. So if you fall behind during the workshop, be comforted by the fact that you can always go back to the video and kind of rerun it again. My pace, I'm going to try, based on the poll too, I'm going to try to go not entirely fast or slow. So I'm going to try to hit this medium where I'm going to assume that you know a little bit about Jupyter Notebooks and a little bit about Python, but you're not experts in either. So that's going to be my pace, and hopefully that will work for majority of you. And I'll stick around afterwards for those of you who have questions. Okay, so in order to get kick-started, in the bottom of the link that I sent you, there's a link to the UCLA Jupyter Hub. If you can go ahead and open or click this link, if you haven't already, I'm going to try to mimic your environment here. You should be welcomed by this big orange button, which you can click, and it'll take you to a login screen. If you are affiliated with UCLA, then you can select, or type UCLA actually in that search box, and it'll be the first option that shows up. And this will take you to the authentication, the two-factor authentication page where you can enter your information here and log in. Okay, so I'm gonna do the same thing that you guys are doing, hopefully. Get my cell phone up and get that running. While I have this running, if you're not, I know there's about 10% of you who are not part of UCLA, use the binder link below here. Forewarning, this binder link takes a long time. So when you click on it, you're gonna have to wait literally about 5 minutes before it loads all the necessary components, the libraries, and gets you ready to get going. Okay, so hopefully we are all on the same page here, and you see the first notebook open on your browser. So I'm going to pause here to make sure that we're all here at least. Okay, and let me know if, or raise your hand. I should also mention Ben Wingham, who you can also see in the participants, is here. And Ben, just a quick introduction, if you don't mind.
Sure. Hi, everyone. So I also work with Yo in the Office for Advanced Research Computing. I do a variety of things, kind of splitting my time between high performance computing on the Huffman 2 cluster, and then doing a variety of education related work, specifically with Jupyter. So I'm the administrator for the Jupyter Hub that you're using. And I teach workshops along the way to kind of related to Python. So I'm kind of more oriented towards this strict Python rather than spatial science. But yeah, if you end up having any questions about the Jupyter Hub environment or want to set up Jupyter and Python related things for yourself, you're welcome to send me an email too. I'll put my email just in the chat in case you want to use it.
Yeah, as UCLA researchers, you're all, we are all available to you, for consultation, for follow-up. And, we're really here to advance your research agenda. And it's not just us, we have a stats team. We're a big team of kind of supposedly experts in different domains here to help students, staff, and faculty advance research. Okay. All right, so I haven't heard any problems, which is great. So I'm going to assume that we can move forward with this. The environment you see here is a Jupyter notebook, a classic Jupyter notebook environment. And it scrolls up and down. It's comprised of these cells that contain either markdown, descriptive text, or they contain code cells. So further down, there are cells that are kind of a little grayish. Those are code cells, and we're going to run these eventually. I have mixed in my entire lecture or presentation here within the notebook, so you'll be seeing a lot of descriptions mixed in with the code cells, which is great, right? Because you come back to this material, you'll be able to read essentially my lecture along with running the code, which makes this environment really, really powerful. Okay, so what I'm going to do is I'm going to go into slideshow mode. You don't have to do this. In fact, I don't recommend you do this. I recommend you stay in this mode and you just scroll up and down and run things along the way. But I'm going to run this in slideshow mode, which is one of the features of Jupyter notebooks. Okay. The content that you'll see on my screen is identical with yours. It's just that I'm in this presentation mode. Okay, so this is the table of contents. Just a quick note that this is currently being recorded. Okay. And yeah, so let's get kick-started. So today's lab is about spatial statistics, and I'm going to cover a very particular method called spatial autocorrelation. The outputs that you see on the screen today are things that we're going to actually produce. And we're going to be working with real data, per se. We're going to bring in data from the LA data portal for arrests. So rather than me providing you with a data set, we're actually going to bring in data in real time. And we're going to create these visualizations based on those data. And we're going to look at spatial autocorrelation. Another way of thinking about spatial autocorrelation is kind of the lack of spatial randomness. In other words, are things statistically significant in terms of their spatial allocation? If you're a statistician, you may be familiar with the notion of things being related to one another based on a value of a variable. And maybe you're wondering whether something is related to another variable based on time. In this time period, if this happens, is it similar to it happening in this other time period? Spatial autocorrelation is similar in that sense, except that we use space. Is what happens here for a particular phenomenon, a variable, similar or dissimilar to it happening in a completely different place? That is what we're testing here, and to provide kind of statistical significance to whether or not things are spatially trending in particular areas. Okay, so one way to think about this is the so-called first law of geography is everything is related to everything else, but near things are more related than distant things. It seems pretty obvious. The graphic that I have here is actually a historical, it's one of the first instances of spatial analysis that's been recorded. And this is John Snow's study on the cholera epidemic in London in the 1800s. And what John Snow did is he mapped the locations, essentially clusters of deaths based on the cholera outbreak. But the legend indicates that they're not only deaths, but there's also the location of water pumps. So it was thought that this kind of supposed outbreak was caused by airborne transmission, kind of like the pandemic that we're going through, when in reality it was coming through the water. And the fact that all these deaths were clustered around a single water pump became the basis of his study that said spatially clustered around a single pump. And the legend of the story goes that they shut down the pump and the outbreak stopped. So that's an example of kind of what we're going to try to do today digitally and statistically with Python. Okay, what are we doing today? The methodology I mentioned, we're going to look at LAPD data. So we're going to bring in data directly from the data portal, from the police department. And we're going to use census block groups as well as this kind of defining boundaries to summarize data by. And we're going to spatially join these two data sets. So we're going to talk about what it means to spatially join. Maybe you've done kind of attribute joins, but we're going to do a spatial join, meaning we're going to join and measure the number of arrests that happen within certain boundaries, which are census block groups. Then we're going to normalize the data. So rather than direct numbers of arrests, we're going to normalize it by population. So we're going to say how many arrests per 1,000 people. Then we're going to conduct global spatial autocorrelation using Moran's I, and I'll explain this later. And then we're going to also conduct a local spatial autocorrelation, which is the fun part because this is where we are able to identify exactly where the locations of these clusters are at. Okay. The libraries we're going to use, so we're in a Python environment. And Python allows you to import libraries, and a lot of these libraries have huge communities behind them. They're very well documented. They're used by millions of people around the world, and these are just a handful of the ones that we're going to use today: Pandas, Matplotlib, GeoPandas. I have some links sprinkled throughout the entire notebook for help and kind of documentations. So you can, click on any one of these links to learn more about, how, visualization in Pandas, how does it work? It works in correlation in partnership with Matplotlib, which is another Python library, and it allows you to produce plots that look like these, very fancy, colorful line plots, bar plots, and what's great about the documentation of all these libraries is that they include a lot of sample code that you can easily copy and paste in your Jupyter Notebook environment and produce the charts that are here. And then it just becomes about you then saying, oh, if I can do this with the sample data, I wonder if I can do it with my own data. Okay, so that's pandas matplotlib. GeoPandas, as the word indicates, is geo, so it's geographic. It kind of leverages on the pandas library and adds a lot of spatial functions to Python coding. It's for a GIS guy like me, it's really awesome to be able to create plots that are map-based with single lines of code. So if you have tabular data that looks like this, and it actually comes with a geometry, it allows you to then build plots that are geographic and spatial and visual in nature. And then you can color the different elements on your geographic visualization based on values in specific variables that might be part of the tabular data. It works with polygons, it works with points, and there's a whole bunch of really nifty things that you can do with GeoPandas. And we're going to cover a little bit of that as well. Other in the statistical side of things, we're going to use two libraries. One is called ESRA. This is exploratory spatial data analysis. This is a sub package of a bigger kind of statistical package called PySal, which is Python Spatial Analysis Library. And it allows us to do some of the spatial statistics that we'll be covering today. And the other one is splot. So this is another library for the local spatial autocorrelation that we'll be using today that allows us to produce these kinds of plots and visual charts of our data. Okay. And so here we are. So we're gonna get started with the kind of coding part of the lab. And I'm wondering, I'm gonna pause here, make sure that everyone's on pace. And if there are any questions, feel free to unmute yourselves. Okay. And, yeah, thank you, Ben, for answering that question. Okay. So all good. All right, so I'm gonna go ahead and get us started. If you are new to Jupyter Notebooks, let me just give you a very quick tutorial. What you have here, and I'll get out of this mode so that it mimics more your screen, so out of my presentation mode. You see that when I highlight a cell, I can highlight any cell. You see the blue bar on the left. It means that that cell is currently highlighted or active. You can click inside of it, a code cell, and select things and actually modify it. Please don't for the moment. But you see this is how you can actually edit and add your own code. To run a code cell, you need to hit Shift and Enter. So either you can have the cursor inside, which makes it active and green, or it can be just selected, which is just blue. When it is selected, if you hit Shift and Enter, it will run the cell, and you see eventually a number appear on the top left of the cell here, which indicates that that number basically says this is the first cell, because mine is number 1, that I have run in this notebook. You don't have to run cells sequentially. You can run them out of sequence, which is a kind of good and bad, sometimes confusing thing, because it's up to you as the person running this notebook to determine how you want to run things. Typically, you want to run them from top to bottom, but there might be instances where you don't. The Shift Enter takes you directly to the next cell. If you just wanted to run a single cell and stay on that cell, it's Control Enter. So I can run Control Enter on an active cell, and it doesn't scroll me down. It just keeps me on that cell. Notice the number 1 has changed to number 2, saying that I've run this cell And that's the second thing I've done in this notebook, number 2. Okay. I know this is review for most of you, but I also know that there's a good number of people who it's the first time. Okay, I'm going to go back in my presentation mode. You should see a number on the top left here. If you don't see a number, it means you haven't run the cell or there's problems. So hopefully you see a number that's either a 1 or a 2. Okay, so that means that we've run all these libraries. There are a lot of libraries in this lab. Pandas, SodaPy, and I'll explain all of these as we go through them. Okay. So what are we going to do? We're going to prepare our data. Again, these are all elements that we're going to be producing shortly. On the left here, this is LA. Hopefully most of you are in LA, but maybe many of you are remote and out of the city. And the boundaries roughly you see here in dark is the city of LA. The crime data we're bringing in is from LAPD in the red dots. LAPD's jurisdiction only covers the city of LA. So you can see little gaps here for Santa Monica and other areas that are not part of LAPD's jurisdiction. We're going to overlay these data sets, right? So it's spatial, one on top of each other. And that's the whole kind of spatial component we're going to be working with. We're going to join the data spatially, quantify them by census block groups, which allows us to produce these choropleth maps on the final output here. Okay, and this is basically part 1 of the workshop, and the part 2 is going to be doing the spatial autocorrelation. All right, so block groups. We're going to be using block groups, which is part of the Census Bureau. The United States Census Bureau creates boundaries for the entire country based on pockets of population counts. So roughly a census tract has about 5,000 people in them, and they're defined boundaries by the Census Bureau, a governmental agency. A block group further subdivides a census tract of about 5,000 people into smaller components. Depending on your research, you might want to use census tracts, which is, again, about the size of 5,000 people. So it's about a neighborhood, I would say. Or you might want to do block groups, which, as the name suggests, is a group of blocks. The granularity of your research might, make you choose one or the other. So if you're working kind of at a tight neighborhood level, you might want to go down to the block group. If you're working at the county level, you might want to stay at the census tract level. Okay. The data we're going to be using, I've grabbed it from a website called Census Reporter. If you haven't heard of Census Reporter, it's a really wonderful resource. It's completely free. Well, census data is free, right? I mean, we pay it with our tax dollars. So if you go to the Census Bureau website, you can download any census data set anywhere in the country. But sometimes it's hard to navigate. So there are these kind of, sister sites or sites built by other either kind of academic or nonprofit agencies that are frankly a lot easier to use. So the Census Bureau website, the Census Reporter website allows you to basically download any data set from the census by just filling in some text boxes. Something like you can fill in, race, and you can, get race tables and then download them for your project. It also comes with a lot of knowledge, right? It tells you, well, how does the census work? This is the actual, if you filled out the census, this is the actual survey that comes in your mail that you hand in. So there's a lot of knowledge here. I won't go into it too much. It's not a census workshop. But the landing page for our data is the total population, very simple, total population by census block group in LA City, okay? And once you land to a single kind of table in the Census Reporter page, there is a very, I think this should be very more prominent, but this is the magic button here, the download data button. You can download it as a CSV file or a GeoJSON file. A GeoJSON file is a format that allows you to work in Python and GeoPandas. It's my favorite format, actually. and it comes with a geometry column. So it's immediately you're able to map this data. I've already included it in our uh, repo that we're using today. So you don't have to download it, but just as reference for your own projects, you might want to know that that's available to you. Okay, the next code cell that's in gray here will bring in that data. So the GPD stands for GeoPandas library. So that's when I did the data importing of the library, I gave it an alias of GPD. So GPD stands for GeoPandas. The dot chains a command saying, hey, we're going to use one of the GeoPandas libraries functions called read file. Very straightforward. And in the brackets, which accepts arguments, all you need to do within a single quotes is tell it where that file resides. Okay. So since I've downloaded and put it in a data folder, it's a relative path from where this notebook is. So it's data slash and then that long name of the GeoJSON file. I haven't changed it. This is exactly what it comes in as from Census Reporter. I'm calling this GDF, which actually stands for Geodata Frame. So go ahead and launch that cell and let's go to the next cell. And let's kind of explore the data that we have currently imported into our notebook. So GDF, Geodata Frame, is the name that I gave this data. The dot head allows us to look at the first 5 rows of the data, right? So here's dot head. For those of you who are new to Python, I'm just kind of going to give you a taste of a few things that you can do once you have data in your notebook. So this is, it's pretty simple. There's only one variable, total population. And as I mentioned, it comes with a geometry column. And there's a GeoID here, which is it's basically a FIPS code, a federal identification code, which we'll be using to as a unique identifier for these block groups. .info, okay, so we're going to run another command. We looked at the first 5 rows. .info is one of my favorite commands because it tells you a lot about the data that we just imported. And not only does it give us kind of the name of the columns, right? So we have the name of the columns. It tells us how many entries there are. It's nice, right? What's the number of records in our table? So we know we brought in 2,516 records. So there, what does that mean? It means there's 2,500 block groups in the city of LA. But there's more stuff here. Like it tells us how many of these rows or columns are null. So if you bring in some other data set and it's kind of messy, there might be columns that have a lot of null values. And it's nice to know that at a glance, right? You might be like, oh my gosh, I'm missing 500 records. So, and finally, most important actually is the data type. So with one command, you can also find out what data type each one of these columns are. So we have an object, which essentially is text. So I know my identifier is a text data type, and I know that my total population value, right, which has to be numeric if we want to quantify it, is in a float. Float means it can also be a decimal, which is great. The geometry column is, since we're using GeoPandas, it recognizes it as a geometry data type, which means that it's, hey, instantly ready to be mapped. Okay. All right, so let's do a couple of other things. We're going to trim the data to the bare minimum columns. So in order to do this in Python, in pandas, you give it, I'm going to redefine it. So I'm going to get rid of a column actually by saying I want GDF to include only these 3 columns. So essentially, what you see inside the outside square brackets is a list, a Python list of only the columns that I want, right? And what that does, and I'm further going to rename these columns. You see what I'm doing here? So I'm doing trim the data to 3 columns, and then redefine the columns. Sorry, rename the columns. So it's GDF.columns to something that's more user-friendly. So total pop, I don't know what B01, I mean, I do know, that's the Census Bureau's table number, but anybody else doesn't know that. it's total pop. Okay, and I'm going to leave the geometry column as the same name. And let's have a look at this data. Okay, so just another command, .head, .tail, shows us the last 5 rows. And this is what it looks like now. We have 3 columns. I got rid of the error column. So we have FIPS code, total pop, and the geometry column now. Now, Census Reporter does something that we all need to be aware of, and that it includes a row in its final row of the table that summarizes everything that you included. So this is kind of good and bad, right? It's great. Hey, I know that the total population of the city of Los Angeles is 4 million people. But it's bad because if you're doing statistical analysis and you don't know that one of the rows is the entire summary, it's going to skew all your data. Okay, so that's what happened to me the first time I downloaded this data. So we have to get rid of that row. Okay, which is great. We learned another Python method here, which is how to drop a column. Okay, there's probably different ways to do it, but if I am outputting the tail and I see the ID number here, I can just drop it with a .drop command. So notice what I'm doing here is I'm redefining GDF to be GDF without the summary row. Okay, I'm not renaming it. I'm keeping it the same. So now that I do that, we have one less record in our table. Okay, one other thing I wanted to do is clean up the FIPS code. So the FIPS code here, as you can see, includes 15000 US. I want to get rid of that part of the FIPS code because a census block group in terms of the identifier actually starts with 06. 06 is the FIPS code for California. So two digits, starts with 0. 037 is the FIPS county code for LA County, right? So we are the 37th county in California. And then what follows is the census tract number in 6 digits. And then the final number is the block group number. Probably too much information. Okay, so we're going to drop the 15000 US. And all we're going to do here is we're going to say, take the FIPS code and replace this part of it with nothing, right? So we're doing a find and replace. And once we do that, you'll notice that the FIPS code now actually only has those numbers in there. Okay. Okay, so one last thing I'm going to do is I'm going to get rid of some values. Okay, and I'm going to use a sorting command. So we have a data. We can sort the values using a sort values pandas command, and I have the documentation here if you want to check it out. The command basically accepts, you have to define, well, what column do you want to sort it by? So I'm going to sort it by total population. And I'm going to output the head, the top 20 rows of the sort. So here, what it does is I have 20 rows showing because I have the 20 inside the dot head. And it's been sorted by total population. What I want to do here is, you see total population 0. So we have block groups that don't have any people in them. You guys know why that might be? Why would there be a block group, a census block group that has nobody in it? Any guesses? Put in the chat. No?
Is it like parts of Griffith Park or?
That's a good point, yes. Although usually the 0 population block groups are, I don't know about parks. Parks are surrounded by housing communities, so I haven't actually seen that. Mountains, maybe, yes. And airports and like Long Beach areas where there's a lot of like boats and you know, the port. There are a lot of huge areas that are kind of industrial or airport facilities that cover a lot of land and have very few actual people living in them. Great. All right, so moving forward, let's subset the data. So we're gonna select a subset of the data frame. And I have a link here if you want to learn kind of the documentation of how to do that. But it's a pretty nifty command, right? So again, I'm going to redefine our geo data frame, GDF, to be equal to a subset of what we already have. How are we going to do that? We're going to say, hey, I want GDF to be all the rows where the total population is more than 100. Does that make sense? So we're keeping everything that's more than 100 in our geo data frame and actually kind of deleting or cropping the rest. Okay. When the data is being cleaned, is the data in actual file being modified? I have a question in the chat. The actual data that you brought in is not being modified, right? So the original GeoJSON file is actually being copied into your Jupyter notebook and it's not modified. However, you created a variable called GDF that includes the data in it. And as you modify it, that variable has now been trimmed and is now doesn't have those records. So if you wanted to backtrack, you're going to have to then start over again. If you need to keep something previously, you might want to change this to GDF2 or something, right? Or GDF greater than 100. But I don't have a need to keep the other data sets, so I'm going to keep it as is. Another question, can I have 1 million records in the data frame? You can. I have worked with 1 million records. It's a matter of computational power. A lot of this happens, it's a balance. The computation will happen in a kernel, which is not part of your computer. But then you might run into memory issues. Just like any other software, the bigger your data, it's going to bog down your system. I would say within this environment, I've successfully worked without any issues with hundreds of thousands of records. I would say beyond that, you run into memory issues or it just starts to bog down the system. Okay, it also depends on which libraries you're using. If you're using JavaScript libraries, then it takes a lot of more resources out. If you're using matplotlib, that is more kind of static results coming back, it might be more doable. All right, so moving on, now I have subset my data to include only records that have at least 100 people in them. Let's do some fun stuff. Let's start mapping this data. Before I do that, our data includes data in a projection that's geographic. It's basically governed by decimal degrees, latitude and longitudes, which are angular units. In order to conduct spatial analysis, or that requires measurements of distances and locational statistics, it is recommended that you go away from angular units, which are degrees, and use a projected coordinate system, right? Which converts your data into measurements of meters or feet, depending on what projection you use it. So we're going to bring our data and convert it into a Web Mercator projection. And GeoPandas provides a really nice, quick, easy way to do this, which is just to say to CRS, coordinate reference system. And you can look at documentations about different EPSGs, which are the codes for different projections. We're going to use a global projection system called Web Mercator 3857. This is also used by a Python library that I'm bringing in called Contextili, which allows us to bring in base maps behind our maps. So we're going to convert our data to Web Mercator, and let's create some plots. For the plots, I'm going to be using this command, plt.subplots. PLT is a matplotlib alias for something called pyplots. And here's the documentation for how to create plots using this command. So it's part of matplotlib, PLT. And as you can see, here are a whole bunch of examples of how to create plots using this method. And it uses kind of this figure axis method of creating either singular or multiple plots in one output. And we're going to do both, actually. Okay. All right. So here's the code to create a single plot. So we have the command here. It generates a figure and an axis. Lines 4 through 8 is the actual plot. Notice that we're prefacing it with our geodata frame that includes the geometry column. And we're going to plot our geodata frame with these arguments. Basically, we're saying AX equals AX, meaning I'm putting this in this plot that I just created, right? And these are some attributes on how I want the geometries to be rendered on the plot. Alpha is opacity, so there's a little bit of transparency in the plot. We're turning off the axis, and we're adding this line of code, which provides us with a base map, essentially. So when you run this, it produces a nice graphical output of our data. So we saw this in tabular form, and now we see it in visual form. So these are the, 2,500? Each one of these polygons that you see here is one of the 2,500 block groups in LA. And moving forward, oh yeah, and I should also mention that the base map you see here in the background, that's produced by this line 14. So it's just a nifty little helper. It's optional, of course, but it just kind of makes the visual much nicer. All right, so now that we have a map of the block groups, let's get some other data. So now we're going to work with the LA Data Portal. So here's the LA Data Portal. I have a link if you've never used it before. A lot of government agencies now provide portals for data that we pay for with our tax monies, right? So they have a whole bunch of COVID and building and safety, water and power, all, and the LAPD as well has data here. If you search for arrest data in the LA Data Portal, you will eventually land on a page that looks like this. And this is a data set from the the department is LAPD. It's updated weekly. No, it's not. They're lying. What? The last update is February 24th. What's up, LAPD? So no, it's not updated weekly. They wish, but I actually check this regularly, and I think it's more like monthly. And they're already quite behind here. It's great. Location is specified, right? And you can look at the metadata. These are all the columns that are associated with this data set, right? So we have the arrest date, the time of arrest, who was arrested, basically, right? The age of the person arrested, the gender, the descent code, which essentially is the race. I want to preface this data set by saying I've worked a lot with this data. This is based on, I don't know if any of you have been arrested, I've been pulled over before, but a police officer will have a notepad in front of him or her and start writing this data in. A lot of this is subjective, right? They don't necessarily ask you, are you so-and-so? So they're gonna have, a lot of this data is based on the police officer's observations. All right, so that's the data that we're gonna be working with, and we're gonna use a library called Socrata. And this is the endpoint of the data that we're gonna be using. Endpoint meaning we're gonna use an API to grab the data from directly from the Open Data Portal, which uses Socrata in the back end to host their data. So this is specific to the arrest data. And you can see all the different things that you can do with the data using their API. These are all the fields. You can query them before you bring it in. You can do a whole bunch of things. There are code snippets in this type of data. And one of them is a Python pandas, right? Very cool. And there's code samples to bring in this exact data set into our notebook. And this is essentially what we're going to do. I've copied and pasted this and kind of configured it a little bit for our lab today. So we're going to use SodaPy Socrata, which is a Python library. Again, I mostly copied and pasted this. I added a where statement. Okay, so I added a where statement to kind of hone in on a specific date range for data to bring in from the LA Police Department. So I'm going to say where arrest data is between July 1st of last year, 2020, to pretty much you know, last January 31st. Okay, so this is like real data, and we're going to bring it in right now. So hopefully this works. Kind of nervous time because this is kind of one of those live dependent things in a workshop. Okay, so that worked. And let's get the information about the data that we just brought in, .info. And these are all the records that we brought in, right? 25 rows. I'm sorry, 25 columns. These are the data types. They're all objects, which is text. They have a latitude, longitude, which is also an object. This we're going to have to change into a numeric. Okay. So let's do. Let's look at the data. It looks like this. This is just a preview of the data. And here's the latitude and longitude columns. And let's just move on. And we're going to massage this data a little bit before we can actually use it. So first of all, the data is in what's called a data frame. It's not GeoPandas yet. So we're going to convert the data into a GeoPandas data frame. And this is the code on how to convert, and I have a documentation for it. So I'm going to convert my arrest data into a GeoPandas data frame by defining the geometry as the combination of a longitude and latitude columns from our pandas data frame. Okay, and then I'm going to convert this to the same projection that we had from the angular units, right, into a web Mercator. And now we have, oh, I'm sorry, final step is to remember the latitude, longitude were objects. We need to convert that to floats. So again, this is the Python command to convert a data type column from something to something else. So I'm going to do as type float for latitude and longitude. And I think we're finally ready to plot it. So again, the same matplotlib subplot code here. And instead of the GDF, which is the block groups, I'm doing arrests and plotting those. This is a point data set as opposed to the block groups, which is a polygon. So what happens when you plot this is that you're going to get a whole bunch of points rather than polygons. So let's see that in action. And oh my gosh, what's happening here? We don't have LA. We have almost the entire planet. And we have a dot here on the bottom right. Anybody know what's going on here? Want to guess? No? No guesses? Why would we have a dot off the coast of Africa? Why was somebody arrested off the coast of Africa? Need to remove it. Yes, mistaken that long. Yeah, no. Those are great answers. It is all of the above. That long were flipped. Actually, Rachel, although that is not what's happening here, that does happen a lot where people mistakenly flip the latitude and longitude and you get things all different side of the world. What this is 0, 0, right? This is where the 0 latitude and 0 longitude meet, right? That's the equator and the prime meridian. And a lot of data, geographic data that doesn't have locational attributes end up off the coast of Africa. Okay. All right, so it's called the 0, 0 conundrum, and we have to fix it. Again, we can subset our data to get rid of it, but let's find out what it is. So arrests and where longitude is equal to 0. And there's a single arrest, a booking, where for whatever reason, the police officer did not include a latitude and longitude or a location. So let's get rid of it. We're going to subset it. Arrests is equal to arrests where, notice the syntax here, longitude is not equal to 0. Nifty, right? So now we're going to just eliminate that record with this command here. And now let's do exact same plot and see if we got rid of that record. Ah, there we go. So that looks much better. It's not, Africa is not part of our map anymore. It's very LA city based, okay? Let's create a 2-layer map. We have the block groups and now we have our arrests. So in order to do that, what I'm gonna do is I want to zoom into the arrests and not to the block groups. So what I'm gonna do here is I'm gonna get the bounding box of our arrests. And there's a nice command called total bounds for a geodata frame. So we can get the total bounds of our arrest data by running that command. And once we have the bounds, we can use that to define how the areas that we're going to plot. And the multi-layered plot is a little longer, right? The code cell is a little longer. So we start with the same thing here, right? But now we have 2 chunks of code to produce 2 layers. The block group gdf.plot ax is ax. The arrests ax is also ax, meaning we're putting it in the same figure, in the same axis. And we're putting them on top of one another. The bounding box code, those numbers that I just got, basically says I want the x and the minimum x and the maximum x, y's to be a certain value. So we zoom into the arrest data and we produce a chart for that. Okay, a plot. Okay, so there we go. Let me just get rid of this. I can see the whole. That's beautiful, right? So we've done a lot of work so far. We've brought in census data from Census Reporter as block groups. They're polygons. We now see arrest data directly imported from the LA City Data Portal. Just the last 6 months of arrests, all plotted on the map. Okay. Any questions so far before I move on? All good? Okay, pace is good. All right. Okay, so now that we have the 2 data sets on top of one another, we need to quantify the relationship between those 2 layers. We're going to do that using something called a spatial join. You can read about how spatial joins are conducted in GeoPandas with the link here. We're going to run a function called sjoin, which does the spatial join. And it's actually a single line of code. Sjoin, what are we joining? So we're going to grab our census block groups, which is GPD, right? I'm sorry, no. This is GeoPandas. So we're going to do sjoin of what? Arrests, and then the block groups. And we're going to go left, meaning that we're going to assign a block group number to every single arrest in our data set. Does that make sense? Okay, so every single arrest, we're going to tack on the block group that arrest happened in. Okay, and so that's what it does. And I do the head. So this is still our arrest data set, right? Booking, the date, where it happened, the latitude, longitude. But if I scroll over to the right, we have tacked on a FIPS code. So now we know where this arrest happened in terms of what block group it happened in. That's really powerful, right? So now we can then quantify this data. Now we're going to do something called value counts. Essentially, we're grouping all our arrests by their block groups. Okay, and we're going to use a command called value counts. And I'm chaining a few things here so that it eventually ends up with a single data frame that looks like this. Super simple. what's the FIPS code? How many arrests fall in that census block group, right? Let's see. Okay, let me pause a little bit here. I have a few questions here. How did it decide on 1,000 the margin to give? Sorry, this was from the previous plot. Pretty randomly, actually. Web Mercator measures things in meters. So 1,000, by padding the X and Y's by 1,000 units means I'm giving it a padding of 1,000 a kilometer, basically, on each side of the map, left to right. So if you wanted more padding, if you wanted 5 kilometers, you'd change that to 5,000. Okay. And then Elizabeth, you're getting an error. I'm gonna have to come back to you on that one. Maybe if you can stay afterwards, I can see if I can help with that one. Okay. Everybody else good? Okay. All right. So now that we have summarized our data, I love that. Let's move forward. Let's create a simple plot. So again, we're going to use a bar plot to plot our data. And what I'm going to do here is I'm going to subset the data and only show the top 20 geographies. So it's :20. There's documentation about that as well. And we're going to plot using a bar plot. And let's see what that looks like. And defining the XY axes. So here on the x-axis, we have the FIPS code. So this essentially tells you these are census block groups. And on the y-axis, we have the arrest count. Very simple, but very powerful, right? So we've summarized all our data by census block group. What this tells me is that there is a single block group somewhere in LA that has 400 plus arrests. So that's quite a lot in the last 6 months. Okay. Okay, so now that we have this single table, what I want to do next is I want to join that table back to our block group geo data frame so that we can map those numbers, right? So we're going to do a join back. And using the merge command, so here's the GDF merge. We're merging the table that we just created, arrest by GDF, on the FIPS code. Okay, so now what does that do is if we look to our GDF, our block group table again, now what we've done is we've tacked on the arrest count to that table, right? So now we not only do we have total population, we also now have arrest count. That's really cool, right? So now we can normalize our data, right? So now that we have total population and arrest count, let's normalize our data. So how many arrests per 1,000 population? And so we're going to do a little bit of math. This is a really nifty pandas method here. If you wanted to create a new column, all you have to do is what's the data frame name, geodata frame name is GDF, square brackets, name of a brand new column, right? Doesn't exist. You just create it here. What do you want the column to be? I want it to be arrest count divided by the total population times 1,000, right? That normalizes our data to 1,000 people. And once I do that, let me sort it and then show you the top 5 census block groups. So here we go, normalized, 163 arrests per 1,000 population. Okay, so here's a little caveat. It doesn't mean that 163 people out of the 1,000 people living in that census block group were arrested, right? They don't necessarily have to live there to be arrested, right? So just keep that in mind. It could be that this census block group includes a park that is known to be a high crime area where a lot of people congregate in, and there's a lot of arrests that happen there. And there might be a pristine neighborhood right next to that park where nobody ever gets arrested. So again, always bear in mind the human element of the data that you're working with. All right, so let's look at this data and actually map it. And what I'm doing here is I'm taking the top 20 census block groups and just mapping it. So essentially what the next map indicates is the location of the top 20 arrest areas in LA City, right? So we're only showing the top 20. So that's kind of a powerful map on its own. Okay, the choropleth maps, again, choropleths are colored maps. So rather than points, we're gonna color each census block group by a value. And this, it's the same thing, gdf.plot. So we created a pretty much a black, gray, transparent one. But by adding a column, right, with a numeric value in it, so we're gonna do the normalized data. And we're gonna give it like a color map that produces a choropleth map, right? Okay. So you can already, just by visualizing this map, see some clusterings happening and so forth. Okay, I'm gonna skip this in low of time because we now go into the second part of our workshop, which is a spatial autocorrelation. Any questions so far? Is everything good? Make sense? Okay, great. Okay, so now we're moving to the statistical analysis part, spatial analysis part. So we have our two data sets. Remember, arrests per 1,000. What we're going to do next is we're going to run global spatial autocorrelation, okay, which essentially is a single number. It essentially tells us globally for our entire data set, are there statistically significant clusters or clustering tendencies in our data, spatial clustering, right? If we have a positive number, it indicates that yes, there is spatial clustering happening. Meaning it's not, you know, if you had a deck of cards and you just kind of randomly threw it on the floor, it's a random, well, maybe that's not random. There's an, okay, never mind. Is essentially are arrests kind of randomly happening in the city or not? Okay, so let's see if we can provide some statistical numbers for that. So global Moran's eye statistic is a way to quantify the degree of this phenomenon. So let's go ahead and see how that's done. In order to run global Moran's eye, we have to first do something called spatial weights. So what we're going to do here is we're going to define how neighbors, how we're going to define neighbors. Spatially, right? If we think about, hey, if a location is surrounded by other block groups, those surrounding block groups are their neighbors. So we need to take into consideration not just that single block group, but what is surrounding that block group into our calculation. How we define neighbors is called the spatial weight. And there's different ways of defining a spatial weight. The method that we're going to use today is one of many different methods, but we're going to use the Kernel KNN weight, which is essentially the nearest neighbor counting based on distance from your block group. And if we say k equals 8, it's going to take into consideration the 8 closest block groups from that block group, from the centroid of that block group. And it's going to count 8 neighbors. And then it's going to average out the numbers of those 8 neighbors and create a numeric value for the neighbors. Okay, so that's what this whole process is going to do. You can learn a little bit more about it in the link provided here. And then these commands are taken from the library that we're using, which is the ESRA library. And so we're going to create the spatial weight and put it in a variable called WQ. And so, okay, so that's the first part of it. Next, we're going to calculate the spatial lag. Let's see. So the spatial lag will actually quantify the neighbors. Now that we've defined what neighbors are, now we're going to quantify those neighbors and average out their values into a single value and put that in its own kind of data variable that we have access to. Okay. So we're creating again a brand new column called arrest per 1000 lag. And we're calculating the spatial lag based on how we define the spatial weights. So all this is done in this code cell here. And when we look at our data, right, now we have total pop, absolute number of arrests in that census block group, arrests per 1000, and now we have a spatial lag here. What does that mean? So, oh, and notice I did a sample here instead of a head or a tail. This is one of my favorite commands because it basically gives me 10 random rows, right? Rather than the top 10 or the bottom 10. So if I run this cell again, it'll give me 10 different random set. So, you know, I just kind of like doing this to get 10 random cells. What is this telling us here? So I know, so I'm looking at, for example, this row here. A lot of arrests, 320 arrests out of 3,000 people. Arrests per 1,000 is 100. The spatial lag column tells me that it's 20. What that means is that this block group has a lot of arrests happening, but the eight closest neighbors average out to have only 20 arrests. Does that make sense? So that is telling you that this is what we're going to call a diamond, right? It's a diamond because it's a super high value surrounded by a much lower value of neighbors. Okay. So that whole phenomenon, the donut and the diamond, let's just, what I'm doing here is I'm creating a new column that basically subtracts one from the other to kind of see where the donuts and the diamonds are. I just want to know, just visually, where are the highest number of arrests as opposed to the spatial lag, as opposed to its neighbors, essentially, and the opposite. So some of these have low arrests surrounded by super high neighbors, right? That would be a donut, right? A lot of arrests happening around it, but inside, right in the middle of it, low numbers. That's a donut. And the opposite is a diamond. And so the FIPS code with the highest negative difference, I'm going to have a look at our donuts, happens in this census tract here, has a total population of 906, very low arrest rate, right? 8. But the surrounding 8 closest census block groups has an average of 76 arrests. That's what the donut is. Okay. On the flip side, what's the diamond in our data, right? That's the block group that it happens in. Total population is 960, so it's very similar to our donut. And the arrest count is 417 people arrested here. Arrests per 1,000, 400 arrests per 1,000. The lag is 90. That's still super high, right? That's 90 arrests in the 8 neighbors that it has. So, you know, just for reference, what I'm going to do next, and you don't have to follow this part because it requires kind of a Mapbox account. But if you have a Mapbox account, you can actually import satellite imagery. So I'm just going to go ahead and get my token. So again, you don't have to follow this part.
Yo.
Yeah.
Hey, sorry to interrupt, Srinraj here. I think your pace was a little bit faster, and I kind of lost you on the donut and
Sure.
diamond. Could you please explain one more time?
No problem. Thank you for that. Let me just, okay, let me just copy that for now. Okay, so let me backtrack a little bit and talk about this output here. All right, so the donut and the diamond essentially takes into account where are there instances where a single entity, we're talking block groups here, is surrounded by dissimilar neighbors, right? So there's two extremes here. You can either be a block group with very low arrest numbers, surrounded by block groups with really high arrest numbers. That would be a donut. You kind of think about it like, oh, it's high values, and then smack in the middle, like a hurricane, right in the middle, very low values. So it looks like a donut. The diamond is the other extreme, right? You are a single census block group with a super high number. And what we're measuring here is arrests. So you have a super high number of arrests in a single block group, surrounded by neighbors that have low or lower, significantly lower arrest numbers. And that's a diamond. Does that make sense?
Yeah, it's clear.
Yeah.
And you were talking about something 8 block groups versus 7 and 6. You were comparing the numbers, right? I didn't follow it. How were you comparing 8 versus 76, 8 versus 420, something like that? When you were explaining, you're trying to compare arrest count versus arrest per lag. So how do you compare that?
To how does this number compare to like the other column?
So basically, I'm trying to understand what is 8, what is 76, and what is minus 67.
Oh, gotcha. Okay. Yeah. So 8, let's look at the stop number. So 8 is the arrests per 1,000. So essentially it is 8 divided by the total population, 906, times 1,000. So that's the 8. So normalize the data to be how many arrests per 1,000 people. So that's that number here. The 76 here is the lag. So it takes, based on the spatial weight that we did previously, it takes the 8 closest neighbors to this block group and the number of arrests there and averages them out. So essentially, yeah.
Justin, sorry to interrupt you. So now you said 8 closest block groups, right? How does the code determine the 8 closest block groups? Where is that 8 block group coming from?
Yeah, good question. It is actually defined here. When you define the spatial weights, right? K and N, closest neighbors, this is where the 8 comes from.
Okay, so it's a static number that we provide.
Yes, yeah. And you can change that number. You can take into account more neighbors or less neighbors, right? There's also other ways to measure weights. There's like the, I don't know, the Queen's method, for example, which is like a chess where it takes diagonal, or the contiguous method. There's other methods, but we're just taking the 8 closest neighbors. And if you look at the documentation here, it'll tell you about the other methods as well. But yeah, it is a static output in the code. Okay, all good?
Yeah, it's clear now.
Great. Thank you for asking the question. What I'm going to do next is kind of optional, so you don't have to follow. I grab my Mapbox. Mapbox, by the way, is a web-based GIS spatial visualization platform. It is not open source, but it provides, if you create an account, it provides satellite imagery that you can use in Python. So I'm going to use my token here, and it's essentially free until you publish something that goes viral and you get millions of hits, then they'll start charging you. You can create an account and use for research. It's mostly going to be free. So I'm just going to run this. Again, you don't have to follow, because I just want to show you what this data looks like on top of satellite imagery. And I'm just going to run a few things here. just to show you, hold on one second, what the data looks like on top of satellite streets. So we're using a plotly command here to plot our, what is this, the donut? This is the donut, yes? So I took in that single block group that I defined as my donut and plotted it on a satellite image so we can actually see where this is happening. Do you guys recognize, any of you guys recognize what this neighborhood this is in? Remember, this is the donut. So this is a single block group that is surrounded by super high, sorry, this is a single block group that has low arrest rates surrounded by super high arrest rates. It is in Venice, yes, so Venice Beach. Have you guys been here? It's a really fascinating area. It's called the Venice Canals. So you see this? This isn't a road. This is actually a canal. And most of the people who live here actually own kayaks and canoes. You know, it's really kind of fascinating. And these are super high valued homes because it's a very unique neighborhood. But it's also in Venice Beach, famous for Muscle Beach. It's a large homeless encampments surrounding here. So it happens to also be a neighborhood that is high in crime. Okay. All right. I shouldn't say crime, high in arrest. There are two different things. Okay. So now also for reference, I'm going to map the location of the diamond. Okay. And this was really surprising for me. Well, maybe not, but the diamond is actually almost in the same neighborhood as the donut, which in some sense makes sense, right? But this is the Venice beachfront area here. And in the pandemic, I actually walked here a couple of months ago. You know, what used to be a huge tourist kind of walkway is now a homeless encampment. There's rows of tents. So it probably accounts for the high arrest numbers. Okay. All right, so we digress.
Sorry to interrupt. Can you go back to the donut?
Oh, the donut map? Sure.
Yeah.
Yeah.
So my understanding is for donut, the center region has the low crime or arrest, and the surrounded by higher, right?
Yes.
So the blue section, which is highlighted, is the centerpiece of the donut?
Yeah, so this is a single census block group. So this is a row out of the 2,500 record table that we had, right? This is a single row that in the last 6 months, which our data is from, it had 8 arrests that happened within this area. The 8 neighbors, closest neighbors, the arrest lag is 76. So the 8 closest neighbors, I don't know, you know, I can't visually see them, but I can kind of anticipate that they're all the surrounding neighborhoods, block groups, sorry, have an average of 76 arrests per census block group. So that's what we're comparing here.
Got it. So the blue is the lowest region, is it?
Yes. Yeah.
Okay.
And vice versa here. This is the highest number of arrests. Diamond.
Gotcha. Thank you.
Okay. All right. So let's create a spatial lag map. Okay, and see what that looks like. So very similar to the other plots that we've created, we're going to create use matplotlib, and we're going to use spatial lag choropleth. So the column here, right? We're going to use that lag column. All right. So let's see what that looks like. All right. So here is our output for that. Okay. So you can see a higher concentration, right? Because now these colors not only represent a normalized count, it represents a count based on its neighbors. So it's kind of statistically incorporating the value of its neighbors in its color. To make this clear, we can create side-by-side maps, right? So I think the code for that is pretty nifty. What we're doing were single plots. So we had 1, 1 in the previous plot. If we change this to 1, 2 when we create the subplots, it means that we're creating 1 row. The 2 is 2 columns. In other words, the plots are going to be on 1 row and 2 plots. So if this was 2, 1, for example, instead of 1, 2, it would be 2 rows and 1 column, meaning the plot will be on top of each other. Does that make sense, right? So 1, 2 essentially says side by side. A 2, 1 would be top bottom. Okay. And what happens here is that the AX where we're positioning our maps into, when we have a 2 here, it creates an AX0 and an AX1. So we're saying on the map on the left, the AX0, I'm going to put the normalized arrest numbers. And on the map on the right, we're going to put the lag map. So I just want to compare the differences between these two outputs. Okay, so as you can see, there's a very significant difference here, in which now on the right here, we see statistically significant clusters based on its calculating its neighbor, the tendencies of their neighbors, right? So these are high numbers surrounded by high numbers. The greens are low numbers surrounded by low numbers. Does that make sense? Okay. Let's see here. How are we doing in time? It's 10:30. Okay, we still have 30 minutes. So I'm going to, I don't know, do we want to see an interactive map of this? Again, this is kind of more for reference. And talking about lag, my notebook is lagging a little bit. So let me exit this for a second. All right, I'm gonna bypass this slideshow mode, which wasn't working. So I'll go scroll mode, just like you guys, okay? Okay, so what I just wanted to show you is an interactive version of this map on a satellite imagery, which again requires that Mapbox account, which you can create later. And if you wanted to see satellite imagery, interactive satellite imagery, you can use it. So let me just quickly show you what that map that we just created with the spatial lag would look like on an interactive plot. So you can run the next 4 or 5 cells until this choropleth mapbox command, which will create an interactive plot. Let's see if this works. I'm starting to run out of memory, so I'm a little bit worried here. Okay, that worked. Great. So it's exactly the same plot, right, that we produce with matplotlib, but it has it's JavaScript, so it's interactive. As I hover over, it tells you the numbers that we're interested in, and it's zoomable too. If you scroll your wheel up and down, you can actually zoom in. Okay, so this is, you know, kind of a visual enhancement. You know, it's pretty, it's nice. You might want to add it in a screen grab of this and add it in a report. But I think for publication purposes, you want to stick with Matplotlib, right? But I like it. It's really powerful because you can see, you know, the built environment behind what's going on, certain neighborhoods, and the Mapbox satellite maps are so beautiful, and it includes labels, so you can actually then identify what areas these things are happening in. So for that reason, I wanted to include it there. Okay, so let's move on to our Moran's plot. All of this work is essentially to get to a single number called the Moran's I value. And once we have the weights defined, and we can actually output a single number, okay? So all that hard work to get to 0.2865, so and so and so and so and so. And that's our global Moran's I value. That is the number associated to the amount of spatial autocorrelation happening in our entire data set. But what does that mean? What does 0.2 mean, right? It's a positive number, right? So the documentation tells us that if it's a positive number, it means that there's positive spatial autocorrelation happening. What does that mean? It means that we do have spatial clustering tendencies happening in our data. And it means that high values are close to high values and low values are close to low values. That phenomenon is evident and happening in our data set. And we can, okay, so what is negative? Is it, if this number was negative, it would mean that there's negative spatial autocorrelation that happens, which is less common, but it means that similar values are far away from similar values. So that's a negative. Right? An example of a negative spatial autocorrelation would be like the locations of hospitals. Because you don't want hospitals to be clustered next to each other. Well, maybe you do, I don't know. Probably you don't. You want hospitals to serve the entire community, right? So you don't want them all clustered in one location where people have difficulty accessing it from far away. So you want to spatially disperse the location of hospitals so that they equitably are accessible to entire communities. And that would be an instance of negative spatial autocorrelation, right? So they're far away from each other. All right. So we can also produce a scatter plot, all right, of our data here. And so this this is essentially an XY of the spatial lag on the Y and the normalized arrest numbers on the X. So there's a strong correlation here, positive correlation that we're seeing. And this chart will look a lot different as we move forward. But what is the significance of that value 3? I'm missing a, well, roughly 0.3. What that means is, oh, and actually, we can actually plot this number here. And this is a nice command here that comes with our spatial library here, that we're simulating randomness, right? So essentially what we're doing here is we're running, so think about it as every single census block group that we have in our data, and we assign the arrest numbers randomly across the board to all these census block groups. And we do that 1,000 times. So we say, okay, randomly assign all the numbers that we have. So taking them out of their census block groups, randomly plug them back into census block groups. What does that look like? So this curve that you see here is the simulation of 1,000 random simulations of our arrest data into the 2,500 block groups that we have. This value here is where our current data lies, which means that we're far away from random simulation of our data, which indicates that we are statistically, significant in its kind of non-randomness, if that makes sense, right? So this is what this is telling us. And this is, many of your statisticians have seen this and know that that value is the p-value is 0.001. So it's a super low number, I guess, p-value. Okay. So yeah, any questions so far on the global spatial autocorrelation? Okay, great. All right, so now we're going to do local spatial autocorrelation. I briefly mentioned the high and low, high, low, high. What I mean by that is now that we know that there's phenomenon that we're looking at, which is arrests in LA City, is not a matter of spatial randomness. Where is it happening and how is it happening? The where we kind of started to see on those maps that we produce. The how, like the high, are high values next to high values, and where are the high values? Where are the low values? Like low arrest numbers surrounded by low arrest numbers. Where is that happening? And then where's the donuts and where are the diamonds? The lows surrounded by highs and the highs surrounded by lows. Okay, and we're gonna do that using local spatial autocorrelation. And so the library that we're going to use is called LISA, the Local Indicators of Spatial Association. And LISA essentially produces the same plot that we produced earlier. Oh, I'm sorry. Right, with the arrests on the x-axis, the spatial lag on the y-axis, but it color codes them based on whether or not it's high values or low values, right? So on the top quadrant here are high values, and the p-value for that is 0.05. So it's only going to color values where the block group has a tendency to have a highly correlated neighbors at a significant 0.05 significant p-value. Okay, same with the blue on the bottom left, the low lows, the high lows, the diamonds, and the low highs, the donuts. So we've color coded these in our scatter plot here. We can also color code these on a map, right? So essentially, if you think about this scatter plot, right, each one of these dots represents a block group. And when we create the map, the LISA map, as it's called, okay, right? It takes the values from that scatter plot and maps them with the same color values here, right? So now what we see here is not only do we see kind of the visualization of the spatial lag, in which we would have to kind of visually determine, oh yeah, okay, so this I see kind of clusters here. Now we can statistically say at a p-value of 0.05, we know for sure that there is high values next to high values in downtown LA at a p-value of 0.05. And the blue areas represent the low lows, so low arrest rates kind of in the Santa Monica mountain areas, surrounded by low arrest neighbors. Okay. And we see some instances in smaller degrees of donuts and diamonds. All right. And just to show you one final plot, the side-by-side plot, comparing different p-values, right? So this is the p-value at 0.05. And this one's the p-value at 0.01, side by side. You would see less instances the higher your p-value is, because you're kind of honing into kind of a higher degree of accuracy in terms of your spatial autocorrelation values. Okay, but there are still areas in LA City where that is true at 0.01. All right, so yeah, that kind of concludes my material for today. I hope that was useful. I think I kind of maybe hurried a little bit in the end, but let's maybe take some time to digest what just happened and open it up for questions if you have any, or comments or thoughts. Yeah, thank you.
Hey, Yo, thanks for teaching this. If you can quickly summarize from the morons stuff, right, what actually we are doing, it will be really helpful.
Yeah, so let's see. Yeah, I can just summarize a little bit, kind of starting with the global Moran's I value, right? So the global Moran's I value is essentially a single value that is calculated because you have assigned the weights already, and you've already created a weight parameter, and it essentially takes your entire data set and calculates the degree of spatial autocorrelation globally that's happening in your data set. So that's just a single number that tells you, hey, you can feed it, any data set, any variable, and it'll tell you whether or not it's spatially autocorrelated or not. It doesn't tell you where things are happening. It just tells you whether or not it's not spatially random. The next set of processes kind of determines to what degree is that true or not. So that number 0.28, you can further kind of validate that number by simulating randomness, right? So you take those arrest numbers, you pluck them out of their associated block groups, and you randomly plug them in to back to random block groups, and you simulate the creation of the Moran's I value 1,000 times, essentially, and it creates this kind of bell curve. And this is where you are. So based on the data that we imported, it tells us that even if you did this 1,000 times, there's no way it could have been within the random simulation, right? And then the Moran psim outputs the p-value that your data is in globally. So we know for sure that 99.9% of the random maps, there's less than 0.1% chance that this happened randomly. Right? The local spatial autocorrelation then allows us to see exactly where this is happening, right? As opposed to just globally, I know that there's this isn't the things are spatially autocorrelated. Where is it happening? The same plot, but now we have color codes on the high, high lows, low lows, and low highs. And then making this into a map, since every single dot here represents a block group, we can map it and assign the colors based on those values. And it produces this map.
So how different is this from the diamond and donut, this particular graph? So this is high arrest rate surrounded by a high possibility of crime surroundings, right? How
Yeah.
different is it from the donut and diamond?
I think they're all kind of related, right? I think the donut diamond exercise earlier was a preliminary investigation, I would say, that I like to do a lot of exploration of the data and assumptions to kind of understand it prior to doing a lot of processes, so that I know that I'm not imagining things. So that was kind of all that was, to be honest. And then also kind of seeing it on top of satellite imagery to kind of validate what I think I am seeing, right? So that because when I see it in that context, I'm like, oh, that's right. That makes sense. The data makes sense. I understand that community. I've walked through that community. I can feel it. So I think I'm on the right track. Because I always fear when I do a lot of these kind of number crunching that I might be doing something wrong, that I might produce something that, doesn't actually make sense when you kind of think about it through lived experiences, especially when you're kind of working with really sensitive data. Arrest data is really sensitive. Crime is really sensitive. And if you designate or if you assign communities and produce reports that say, hey, this community is ridden with this kind of phenomena, you're responsible for that statement. So to be honest, that's kind of where I was going with that. And I think this whole process below, takes statistical methods and kind of validates it through sound statistical methodologies that are practiced in the field.
Got it. Makes sense. Thank you, Yu.
All right. Well, you know what? I'll conclude the workshop here, but I'm happy to stick around and talk to any one of you if you have questions about your own data, about your own research. I'll stick around for that. For now, what I'm going to do is I'm going to stop recording. Okay.